No, sir.
Okay, so what we were doing, we were understanding that what is the microscopic form of Ohm's law, right? So, firstly, let me quickly revise what we did so far. So, we learned that whenever charge is flowing, right? So it produces current, and it has two kinds. One is steady current, which means that equal amount of charge is flowing, right? But realistically, it cannot happen, right? It cannot happen that whatever charge is flowing and you get the same charge. Yeah. So just see the example of lightning, right? So you get different amount of charges flowing. So there are two kinds of current. One is the steady current, and the other one is the non-steady current. So for steady current, we saw that I was current was just charge upon time, right? And then we saw that yeah. So then we saw that for, let's say, if charges are not equal amount of charge are not flowing, so we take some portion of charges flowing this through some area, right? So let's say that this is some area, and delta q amount of charge is flowing, right? So let's say it is flowing this way. Then we said that the average current, right? So this was how much? This was delta q by delta. And then we also saw that what is the instantaneous current. So current at a specific point of time. This was small change in charge and small change in time. So this we studied, and then we saw that what is, so what happens when the charge is going through some conductor, right? So let's say we have a charge, right? We have a conductor, and there is nothing, so there is no external field. So we saw that charges are moving in random direction, not this charge is moving in this direction, this is in this direction, this direction, this direction, right? So they were randomly moving and colliding. So what happened was that their average speed was zero, right? Then what we did was that we applied some external. So we joined this to some, right? Then there was this, so the current is flowing this way, which means that charges are flowing this way. Electrons are flowing this way, right? And then we saw that what is the drift velocity. So this came out to be n tau, right, by m. So this we saw, right? Or is this we got? So this was yeah. So no, not this one. So we found out that this is tau by, right? And then we found out that what is the amount of current that is flowing. So we found out that relation between the drift velocity and the current. So this came out to be NEA, right? So this was what we did in the previous class, right? Where this is the number density of the electrons that is flowing. This is the charge on one electron area, and this is the drift velocity. So this is the relation between the drift velocity and this current. Okay, now and then we studied about the Ohm's law. So in Ohm's law, we saw that whenever we plot the voltage versus the current plot, so then we get a straight line, which means that V is directly proportional to I. So which means that we remove the proportionality, so then we get a constant which is called the resistance. So resistance meaning it opposes the flow of the electrons, right? So it is the opposing force which, so whenever the electrons are moving, charges are moving, so it just oppose the motion of those charges. So this was about the resistance, right? And then we saw that there are some materials which doesn't follow the Ohm's law, right? So that is called the limitation of the Ohm's law. In that, we saw that we can have these kind of variation, right? And we can also have these kind of variation. So different variation we can have, right? So they don't follow the Ohm's law. So V is not directly proportional to I for the non-ohmic material. And what are the example of non-ohmic material? The example are semiconductor and other devices, right? Other materials. So this we also learn, and we also learn what? We also were doing the microscopic form of, right? So this we will do. And we saw that what did we use? We saw that current is NEAVD. So what we did is that we take this area in this side. So this becomes A and this is NE. So this is called the current density. Current density, and this is represented by J. So J is NEVD. And now when we put the value of VD, so this becomes NE and this is EE tau by M. Okay, so then this becomes what? This J becomes NE square and tau by M and then so we say this term or this term is called the conductivity. This term is called the conductivity, and this represents that how conducting our material, right? So this is represented by sigma, and so this is called the microscopic form of okay, microscopic form of and the inverse of or the opposite property of the conductivity is what? So what is the yeah, I got yeah. So what I was talking about that what could be the opposite of conductivity, guys? What could be the opposite of conductivity?
Resistivity.
Yes, resistivity. Right. So we have one thing which is conductivity, and then the other thing which is resistivity. Right. So this is represented by rho, which is 1 by sigma. And we know that what is the value of sigma? So sigma is n and then e square tau by k. So this conductivity would be what? This conductivity would be, or this resistivity would be 1 by sigma, which is m by n p square by tau. Is this clear, guys? This is the resistivity of the material. Okay, understood, guys?
Yes, sir.
So please note down this part, right? And then I will talk about the resistance, resistivity, and the variation of or the temperature dependence of resistance and resistivity. So please note it down, and then we'll talk about the next one. And this part is only derivation, and there are not a lot of question based on this, but because all the question are from the combination of resistances and the cell EMF combination of cell and temperature dependence. If you guys have any doubt, you ask. Otherwise, and whenever you guys need me to scroll down the screen, tell me that. Yes. Yeah. So you guys see that this current density is proportional to this electric field. And you see that this conductivity is dependent upon these scalar terms. So you have a vector in the form of electric field. So you see that this current density, right, this current density is a vector, but your current is not a vector. So just remember. Okay, noted, guys.
Yes, sir.
So, and this tau is what, guys?
Relaxation training.
Yeah, so this is the relaxation time between the collisions, right? So time between the collisions. So if I increase the temperature, what will happen to the relaxation time? Will we get more relaxation time or will we get less relaxation time? What will we get? Just imagine that there is some conducting material, right? And there are some electrons. And what you do is that, so the electrons are moving, okay? And what you do is that you increase the temperature. So will the time between the collision increase or decrease? So will the electrons get more time to relax or not? Just see the term relaxation. So will they get more time to relax if I increase the temperature?
Yes.
Okay, so think it this way. That if I increase the temperature, then the kinetic energy of those electrons will increase, right? So they will move faster and faster, right? and they will continuously collide. Before the increase of the temperature, they will collide, right? So they were colliding and taking some time, right? But what we did was that what we did is that we increased the temperature. So we increased the kinetic energy. Now the charges are colliding faster. So they will not get so much time to relax, right? So is that clear? Yeah. So if I increase the temperature, then they will get less time to relax. Okay. So then they will get less time to relax, which means that this rho will increase. Understood? This resistivity will increase. So if I, let's say for the case of drift velocity also. So this was what? This was E tau by m. Okay. So this drift velocity is also dependent upon temperature. So if I increase the temperature, right? If I increase the temperature, then this relaxation time will decrease, which means that my drift velocity will what? This will also decrease. Okay. And when I increase the temperature, relaxation time decrease, and my resistivity will what? Resistivity will increase. So these are the things that we can tell about the temperature. Okay. So we'll talk about the temperature dependency next. So let us talk about yeah, resistance, right? Resistivity and temperature. Okay, so yeah, we already know that this resistance is what? This is the opposing which, or this is not actually, but this is so this is a physical quantity which opposes the motion of the charges, right? And this is dependent upon the length of the material, right? This is also dependent upon the area of cross section of the material. Okay, and this is also dependent upon the nature of the region. So R is directly proportional to L. R is inversely proportional to A, right? So if we remove the proportionality, right? So let's say that this is L by A, right? So what if I remove this proportionality? So we have a constant which is called the resistivity. Right? So this we have learned in the chemical. This is called the resistivity, and it is only dependent on the material, right? So okay, so this is dependent upon temperature, right? Now we know that yeah, so we know that how much is R. Okay, so how this resistivity is dependent upon temperature. But before we do that, let us do one question. So if the length of the wire is decreased by 25% and area is increased by 25%. Okay, so what is the new resistance? Okay, so what do we know? Right. For the let's say that the previous case, this was the length of the wire and this was the area of the cross section. This was the so R was what? R was simply rho L by right, and this is the same material that we are using, right? So what we did was that we just decreased the length by 25%. So we decreased the length by 25% and we increased the area by 25%. So let's say that this new area is A prime and this new length is L. Okay. So and the material is same, right? So the R prime would be what? This would be rho L prime by E prime. Okay. Now what is the thing that we need to calculate? So we need to calculate what is L prime and what is A prime, right? So this is decreased by 25%, and this is increased by 25. Okay. So now let us find the L prime. So this was L, but decreased by right 25% of L. Right. So this is L minus 25 by 100 L. So this is 3L by okay. This is 3L by 4. Oh, who got disconnected? And now what was the new area? So this is increased by so A plus 25% of. So this becomes what? A plus 25 by 100 into A. This is this 4. So this is how much? 5A by. Is that clear? So now R prime would be how much? This would be rho and L prime is 3L by 4 divided by A prime is 5L by 4. So, oh, A by 4. So this is rho L by A and this is 3 into 4 divided by 5 into 4 cancel and this is R. So our new resistance is how much? This is R and this is 3 by 5. This is our resistance. Any doubt in this question?
No,
Yes.
sir.
Yeah. So Please note it down. So this was the similar topic that we did in the 10th class. Just repetition. Yes, this is looking absurd. So let us write it in property of material. Done. 5 R by oh, 5 R by 3. How did I? Okay. So 5A by 4 and 3L by 4, right? So this is 3. So in the numerator you have 3, right? And this is in the denominator. So how will we get 5R by 3? You see in this way that we are decreasing the length. If we are decreasing the length, then resistance will increase or decrease, sir. Yes. So that will, oh, okay. So yeah, please note down, guys, and then we'll talk about temperature dependence of. And please be there for the class assessment. So that would be on resistance, Ohm's law, resistance, and what? And that temperature dependence. No, not temperature dependence. Only Ohm's law, resistance, and resistance. That question. Find that question. Uh, yeah, noted, guys. Should I scroll down this screen? Yes, should I scroll down the screen, guys?
Yes, sir.
Whenever you guys need me to scroll down, it's Yes, noted, guys. There, there can be other kind of question. Let's say that length is increased by 2 times. So I showed the question in the percentage form. So what they will do is that they will write that, let's say that length is double, area is half, these kind of questions. So what do you do is that just diagrammatically represent those situations, right? And write the relation between those length and distance. So then the question will be yes, done, guys.
Yes, sir.
Yes, Saad, noted.
No, sir.
Yeah, did you say yes, sir?
No.
Okay, please. Note it down. What is happening, Saad?
Sir, that was my small sister, sir.
Yeah, no, that's the gout. Gout.
Yeah.
Okay, noted.
Done, sir.
Yeah, sir. Done.
Now the next topic is the temperature dependence of the resistivity or the so they both have same dependence on the temperature. So let's say if I talk about resistivity, so this is equal to rho naught. Let's say this is at some temperature, and this is 1 plus alpha T minus. This is how the resistivity is valued, and same goes for the resistivity. This is also a very like 1 plus alpha. This is the temperature dependence of this is how the temperature is compared. The resistivity is temperature. And yeah, what can I talk about? So let's do one question to understand that. But before we do that, what is the graph? What will be the graph of these two equations? What will be the graph? Can you guys identify that? Let me write it in this way so that you guys understand. Let's say this is y, this is y naught 1 plus alpha x minus x naught, and where this alpha is temperature or coefficient temperature coefficient of it. Yes. So, guys, what would be the graph of this equation? Can you guys tell? Yeah. What would be the graph of this equation? Any idea? So, let me give you a hint. What is the degree of this equation? Yeah. What is the degree of this equation? Let me simplify this and let's say that you guys are by this is y naught 1 plus alpha x minus alpha x naught. This is y naught right is equal to 1 plus alpha x minus alpha x naught. So let's say this is by equal to this is ax minus let's say 1 minus alpha naught c. So ax minus by minus c equals to 0. So what is this equation? Yes, yes, guys. What is this equation? Guys, remember this equation. Ax plus y plus is this equation not complete? Yes, guys.
Linear equation.
Yeah, linear equation in two variable, right?
Yes.
So yeah, linear equation represents what? A straight line, right?
Yes.
So the graph of these two, and in here y is what? So this is y, right? So the graph of these two equations would be a straight line. That is what I wanted to do by writing. Okay. So the graph of these two equations would be straight line. So how the resistance or resistivity would be proportional to the variation of the temperature. Okay, so they will vary linearly. Is that clear? Yeah. Is that clear?
Yes.
And one thing which is very important to remember, yeah, one thing which is very important to remember is that this T minus T naught is very small, right? Not very small, but it is small. So we are talking about the temperature dependence in a very short range, right? So in this range, this behaves like a linear equation. So these equation holds for a very short range of the temperature variation, right? So if we change the temperature from 0 to 50 Kelvin, right, then the difference would be more. So they will not follow this linear relation. We will talk about those relations for different scenarios. Yeah, so but let us do one question based on this property. So let us do one question and then it would be clear to us. Question. What is the question? Yeah, so and this is the example of NCRT. So the at room temperature, so at room temperature T naught is how much? This is 27 degrees, right? And the resistivity is found, so it's resistance. So they found the resistance at this temperature, which is what 75.3. Okay. Now when the toaster is connected to supply, the current settles after a few seconds to a steady value of 2.68. What is the steady temperature of nichrome element? Okay, so this is a different question, right? So we need to calculate when the toaster is connected to now. So this was the initial condition, right? Now toaster is connected so to a voltage supply. Now so the voltage is how much? Voltage is 230 volt. Okay, and it is connected to what? So the current is then 2.68 ampere. Okay. So after some time, the current is 2.6 ampere, and what is the steady temperature of nichrome element, right? So they want us to calculate what is T2, okay? And yeah, I have not written T, so what did I write? I have written T minus T naught. So, yeah, this is T. And the temperature coefficient of resistance of nichrome average over the temperature range is always. So alpha is 1.70 into 10 to the power minus 4 degree per degree. So this is the question. We have a toaster, right? So the toaster is of the temperature of this 27 degrees C and resistance of the toaster is 75 volt. Now some voltage is applied, right? And after some time it was found to be the current of this toaster is found to be 2.6 ampere, right? So now they are asking that what would be the temperature at this state, and they have given the coefficient of temperature coefficient of resistance is this much, right? So we have the initial temperature, initial resistance, and the coefficient of resistance, and they are asking about what is this temperature. So what do we know? We know that R is R naught 1 plus alpha T minus T, right? So we have this quantity, we have this quantity, and we have what? We have this quantity alpha. So we have to find this, right? So this should be okay, guys. So I got disconnected. Yeah. So I was telling that at which point I got disconnected. Please, can you guys tell me at which point I got disconnected?
So you were telling the demand.
Yeah. So I was talking about that this initial resistance is given, and the initial temperature is given, and the temperature coefficient of resistivity is given, or the resistance is given, right? And they are asking about the temperature after it has achieved this current, right? So, but they have not given this R, right? So how can we calculate this R? How can we calculate this R, guys? Just look at these two. So how can we calculate this R? Right. So first thing is that we need to calculate this R. So this should be V by R. Right. So this is 230 by what? 2.6. So R would be how much? This would be 230 by 2.6 is how much? Is 30 divided by 2.6. This is 88.46 and 15. So you guys see that due to the temperature difference, the resistance has increased to this value. So this is our new resistance, right? And now we know R naught, alpha, and T naught. So you guys please calculate and tell me what is T. You guys please calculate, put all the values and tell me what is the answer. Quickly you guys calculate. Yeah, so let us keep this to 3 decimal places. Let's say that or 2. So you guys are you guys calculating?
Yes.
Yeah, please calculate and tell me. Yeah, what it is. Even you guys get the answer, please. You guys can use calculator. Yes. What did you guys, Saad and Aisha, what did you guys get? Got any answers, guys? We also solve this problem and you guys check your answer. So R is R naught and 0.845. Yeah, so approx 845. What is that? Got disconnected. Yeah, Saad got disconnected. So let me check your answer. 1 plus 1 plus alpha t minus t. Right. So R is 88.462 divided by this is how much? 75.3 and this is 1 plus alpha t minus t. So this is how much? 88.462 divided by 75.3. This is 1.174 minus 1, which is equal to alpha t minus t naught. So this is how much? So this is 0.174 and equal to alpha is alpha is 1.7 into 10 to the power minus 1.7 into 10 to the power minus 4 t minus t naught. So this is 0.174 into divided by 1.7 into 10 to the power 4 t minus. So this is how much? 0.174 divided by 1.7, 0.102, right, into 100, 1023. Okay, this is a very huge number. This much change in temperature. Did we do anything? Yeah, so 230. So let me check yeah, how much we are getting. Get 847. Yeah, your answer is correct. 847 is the answer, right? And I guess that there is some, yeah, so you guys check and 847 degrees C is the T naught. So the new temperature is T is equal to 847. Yes, Aisha, you are correct. And yeah, Maria. So at which point you got disconnected, Maria? Yes, Maria. At which point you got disconnected? So you guys please note down from here. Okay, so please note down from here. Did you guys note down this part? Okay, finding T. So did you guys note down this part? Temperature dependence? Yes. This part did you guys note it down?
No, sir.
Yeah, so please note it down and we will do the next one. Guys,
Done, sir.
And that's also yeah. Okay. Different, was the temperature difference. And this part is where this is wrong. So that is, that Aisha.
Yes, sir.
Okay, so the next topic is
Sir, your voice is not clear.
my voice is breaking.
No, it's not clear. It's like muffled.
Oh, is that clear now?
Yes.
So now we have yeah. Now we have for a small change in temperature, right? So for a small change in temperature, it behaves like a linear equation. But for different materials, okay, different materials shows or different materials show different variation of temperature dependence. So this is just for the yeah. This is not that important. Just this is just for the knowledge purpose. That for conductors, this is how the temperature, this resistivity varies. So this is how the resistivity of the conductor varies with the temperature. Okay. So you guys can see that this is not linear. Okay. So this is not linear, and this is a conductor. And you have a different material, right? So for alloy, this behaves like this. So this is an alloy. And yeah, my voice is breaking. Am I audible clear now? Yeah, am I audible now?
Yeah.
Yeah. So, and now for the semiconductor devices, right? So this is totally opposite. Okay. So this is we can see that this is decreased. So this is for conductor, this is for ally, and this is for semiconductor. So this is how the variation of the resistivity happens with the increase in the temperature. So we can see that for the case of conductor and alloy, the resistivity is increasing, right? And for the case of semiconductors, we see a very different variation of resistivity. So this is, yeah, this is only to, right? So it is not that much important. You guys, please note down this one. So in 1 or 2 marks question, they can ask you this, right? And you can also think this way that if you have a conductor, right? So conductor will have a good conductivity, right? And if you have insulator or a semiconductor, so it will have a good resistivity. So that is only the difference. Okay. Yeah, noted, guys. Okay, now let us talk about the combination of resistance. So now we have talked about all these, right? Resistivity, resistance, drift velocity, and current, and all things, Ohm's law. Now let us talk about the combination of resistance. Right. So we have two kinds of combination. One is the series, and the other one is parallel. Just take the analogy from the capacitor. So in series combination, in there we had what constant? Charge constant. So in there we will have current constant. And in parallel we have voltage constant. Right. So this is yeah. So in combination of resistance, we already know that. Let's say that if we are we have these kind of resistance, right? So when we connect end to end, right? So this was the start, this was the end, and then we start and the end. So when we connect from start to end, right? So this is called the series combination. And when we connect, let's say in this way. So this was the start, right? So one side, right, attached to this point, and the other side attached to the other point. So then this combination is called pattern combination. Next, this is series one, and this is the pattern. So for series one, what do we have? For series one, we have current is same, right? So this has I, and this has I, right? And voltage would be how much? This would be V1 plus V2. So from Ohm's law, we know that V is IR. So this would be, this is, let's say, IR equivalent, and this is IR1 plus IR. I cancel, and we have R equivalent is R1 plus R2. Similarly, what do we have for the parallel resistance? So for parallel resistance, our voltage is same, but current is different. So current is I1 plus I2. So then we know that this is V by R equivalent, and this is V by, let's say, R1 plus V by R2. So V cancel, and we have R. So this we have already done in our initial 10th class study class. Just the division of that one. And what we will do is that we will add some more devices. So in there we only had resistance. Now we will add capacitor and cells and all the other things. And then what we will see that what is the equivalent resistance and capacity. So just a quick revision, you guys please note it down. And we will do some questions, and then I'll talk about power and EMF offsets. So let's see if we have time, and yeah, let's see if we have time. Otherwise, we'll talk about EMF. Yeah, so Mariam and Aisha, for the capacitor one, what was the equivalent capacitance in the series? In the series combination, what was the equivalent capacitance?
1/C.
Yes, yes, yes. So 1 by C, that was 1 by, yeah, this was for series, and for parallel, this what was. So you see that for the case of resistance, it is almost the opposite, right? Yeah, good. So you guys quickly note it down, and then we'll do some questions, and then we'll start with power and EMF offset. What is it? There is a lot of connectivity issues that we have. So whenever you guys have noted it down, yes, guys, completed.
Yes.
So let's say that I want to calculate the equivalent resistance. Let's say that I have this one, okay, and so what I want to do is that I want to calculate the resistance between, let's say, the A and this B. Okay, so let's say this is 3 ohm. Let's say this is 1 ohm, this is 2 ohm, and this is 5. Okay. So first we will solve the pattern one, right? So in this part, so we have these points, right? This point and this point. So this is parallel to this one, right? Is that correct, guys?
Yes, sir.
So for the parallel case, the equivalent resistance is how much? For the two resistance, it is R1, R2 divided by R1 plus R2. So this would be 1 into 2 divided by 1 plus 2. So this is 2 by 3. Right. So now what is the equivalent diagram? So equivalent diagram is this. O, then we have, yeah, then we have, what? So then we have 2 by 3 ohm, and then we have 5. So this is point A and this is point. And now this is the whole setup in series, right? So then this would be how much? This would be 3 plus 5 plus 2 by 3, which is how much? 8 plus 2 by 3, which is 24 plus 2, 26 by 3. So 26 by 3. I'm really sorry, I keep getting my Wi-Fi has been. Yeah, yeah, I can understand because my Wi-Fi is also giving some problem. So I talked to the operator and then they are, yeah, okay, no worries. No worries about that. Yeah, so is that clear to you guys? Clear, guys? Yes, 90% of the data I'm using from the mobile. So I'm using the Wi-Fi from the mobile because my Wi-Fi is not working from. Do you guys have any question? And if not, you guys please note it down, and then I'll give some complicated questions. So I will talk about the power and EMF of the cells in the next class. So then we will have only few topics left. The combination of cells, Kirchhoff law, and Wheatstone bridge. So only three or four topics. Then this chapter would be complete, right? So Aisha and Mariam, can you go? Sorry to ask you again. So Aisha, in your school, they have completed how many chapters they have completed? Aisha,
Up to the fourth chapter.
so they have completed 4 chapters. Okay, what? Yeah, and okay, so your school will reopen after 23 or 20. Yeah, obviously, obviously, be able to complete. And Mariam, how many chapters for you? They completed. Okay, so for you also they have completed. Yeah, so you can see that we would be completing this chapter pretty soon, and then we will also be completing. Noted, guys. Did you guys note down this problem?
Yes.
Okay, so let me give you guys one question, and you guys solve. So we have, let's say, we have this one, one, and this one, and let's see this point. Okay, this is 2, 3, 4, 1, 2, 3, and yeah, so 4. You guys quickly calculate and tell me the answer. Okay, quickly calculate. You guys have 3 minutes. Quickly calculate and tell me the answer. And you guys remember that you guys will have a class assessment test on Ohm's law and resistance and resistance. So that would be the class test. Yeah, please quickly calculate. Aisha and Mariam quickly calculate it. What is happening with the mobile? Whenever you guys get any answer, please write it in the chat box or tell. Got any answer, guys? This one, right, and this one is let's say 1/r by 1/1 3, 4 LCM is how much? 1, 3, 2, 10, 2, 1, 1 to 12. Right, and this is 6 plus 4 plus 3. This is 13 by 12. So this is R equivalent is 12 by 12 for this one. So we have 12 by 13 ohm, and then we have what? So for these ones, so this is series 2 and 3. So 3 ohm. So R equivalent would be 3 into 3, 3 plus 9 by this is 6. So 3 by 2. This is R. So we have this 3 by 2. So what would be the equivalent resistance? This would be 12 by 30 plus 3 by 2. So 26, 24 plus 39. So 3 and 63 by 50. Right, so this is the equivalent. Are you guys getting the same answer? Or is there any mistake in my calculation? Any of, yeah, yes, guys. Point 42. I got, yeah, I think I got the same intent. Yeah, so 26 2, yeah, I guess, okay. Okay, I guess, yeah. What is 63 by 20? Let me check that. 63 divided by 20. Yeah, 2.1. Yes, Aisha, you are correct. And Mariam, did you get the same answer? Yes, Mariam, what did you try? Yes, Mariam, did you try at least? Okay, if you have not tried, so please. Okay, one you got it. Ah, yeah. So the rest you please note it down. And Aisha, in the meanwhile, you just log into your login Learnivio account. Okay, you just
Okay,
log into
sir.
your yeah, log into Learnivio account, and then you'll find the class assessment test. Yeah, please take that. And yeah, so hopefully in the next few classes, the classes will be able to complete this chapter also. Okay, good, good, Mariam. So you also please go into the go into the learning account and take that test. So the test would be on what? Test is on Ohm's law, resistance, and resistance. And if you guys find any problem in any question, so you guys can also. Aisha, did you start the test?
Yes, sir.
Mariam, did you find the test? Yes. Okay. So please, yeah, start it. And, by left, you have power and the EMF composition of the then Kirchhoff law and then uh, whenever you guys have completed the test, so that you can. I'm waiting for the others to join. And not disturb the live. Uh, Yes, hello, Rifa. Hello, Rifa. Assalamu alaikum.
Hello, Walaikum Salam.
Okay, so let me talk to the Learnivio team so that Yes. Okay. Oh, where did Rifa go? Yeah, Aisha and Mariam, you guys please join that with another. Okay.
Yeah, it's fine.
Yeah, please join the other. Yes, Aisha, please join the other. Okay, so yeah, Rifa. We completed. Yeah, we completed that. Yeah, we completed the quadratic equation, right? Rifa? Yes, Rifa. So we completed the quadratic equation, right? Your voice is not audible. Please, can you check your mic? Yeah, please check your mic. Your voice is not. Yes, hello, Mayam. So why are you joining this class? Did you not take the test, Mayam? Oh, no worries. Okay, okay, good, good. Bye, Mayam. Bye. No. Hello. Yes. Okay. Yes. Yes, Rifa. Is that you? Hello.
Yes, hello, yes. There is internet problems, that's why.
Yeah. 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 I can. Changing weather, right? Due to cloud, there would be some internet. Okay. So yeah, we finished the quality equation, right? Now we were about to start the linear equation, right? Okay. So let me write here. We have a linear equation in two ways, right? So first thing to note is that linear, right? Linear equation, and then we have these two ways, right? So if we have a linear equation, then what is the degree of that equation,
One.
right? So degree is one, but we have two variables, right? So let's say x and y. So we have two variables, and the equation is this. So there are two ways that we can represent the linear equation. One is the algebraic one, right? And the other one is this graphical. So what would be the graphical representation of a linear equation? So that would be a straight. So let us first talk about the algebraic equation. So the general form of a linear equation is what? Yeah, general form of a linear equation. This is what? Ax plus by plus c equals to, where a, b, c are coefficients and constants. So a, b, c are coefficients and constants. Okay, and x, y are the understood, Rifa? Yes. Is that clear, Rifa? Hello. Yes, Rifa, is that clear?
Yes, understood.
Okay. So now we can see that what is the degree of this equation. We have one degree, one degree. So degree is one, which means that this is degree is one, which means that it is linear. And we have two variables, x and y, which means that they are two. So this is the algebraic representation of linear equation. Okay, linear equation in now let us talk about the graphical representation. So we know that the graph of this equation would be a straight line. So this would be a straight line, right? And if we want to draw a straight line on the graph, So we want to draw a particular straight line on the graph. So how many points do we need? Yeah. How many points do we need?
2.
That's right. So if we have 2 points, then we can draw a straight line. Right. So that is why we need 2 points to draw a straight line on the graph. And on the graph, there would be locations. So there would be, let's say, X and Y location. And let's say this would be X2 and Y2. Let's say this is X1, Y1, and X2. So these two different location points, and we can then draw a straight line. So whenever they want us to represent the linear equation in two variables graphically, so then we will need 2 points, right? We will find 2 points and then plot it out. So generally what people and what I also do is that I calculate the points points at x equal to 0, and this is 1 point, and second point is y equal to 0. So x equals to 0, we will have some y, and y equals to 0, we will have some x. So this is generally people. They calculate the 2 points at x equal to 0 and at y equals to 0 to make the graph simple. Okay.
Okay.
Yeah. So the first part of this chapter is representation. That we already talked about. Algebraic one and the what graph. So let us, okay, and before I do that, so this was about the representation. Okay, and then we have two variables. So then we require two